Many old clocks rely on a pendulum to keep time. The pendulum swings back and forth. This kind of movement is an example of simple harmonic motion. This type of motion is seen in other physical systems such as springs. Motion in such systems is characterized by oscillation back and forth through an equilibrium point. The equilibrium point is the point of rest when the system is not oscillating. For example, in a pendulum, the equilibrium point is the lowest point through which the weight swings. When the pendulum is at rest, it sits at this lowest point. A simple harmonic system has an equilibrium point because of a force that restores the system to its lowest energy. Likewise, when a pendulum is pushed away from its rest position, the restoring force of gravity always causes it to return back to the rest position. Friction will slow it down. That's why you have to keep pushing a swing to maintain the back and forth motion. Likewise, when a spring is pulled or pushed from its rest position, the reaction force causes the spring to return to its original length. The back and forth oscillation of a simple harmonic system can be described by its periodicity and its displacement, the degree of movement. The period t is the time for one complete oscillation back and forth. Amplitude A is the maximum displacement of the system from rest. Over time, the plot of change in amplitude is a sine wave. The period does not depend on amplitude of oscillation. For a spring, the period of oscillations depends on the spring constant K and the mass attached to the spring. For a pendulum, the period depends on the length of the pendulum and the strength of gravity. The period of a simple harmonic system is the time taken for one cycle. Frequency is the number of oscillations per second. Frequency is the inverse of period, that is, F equals 1 over T. Many applications of simple harmonic systems exploit their energy. For example, when a clock spring is wound up, it releases its energy to power the clock mechanism. The stored energy is potential energy. Clock designers and other engineers need to know how much energy is stored in a spring. Simple harmonic systems obey Hooke's law. This law states that the force F, by which a spring is extended or compressed, is proportional to the distance, x. The constant K depends on the stiffness of the spring, which in turn depends on the material from which it is made. The potential energy in a stretched or compressed spring is 1/2 times the spring constant K, times x squared, where K is the spring constant and x is the displacement of the spring, or the amount it is stretched or compressed. During the oscillations, the potential energy in the spring is converted into kinetic energy and back again as the spring goes back and forth.